and welcome to my final presentation for CPE 187 Embedded System Design for summer 2025. My name is Craig Bobian and this is my project, Breakout. For those you don't know, Breakout is a 1976 Atari video game, as depicted here, where the premise is to hit the ball with your paddle and take out every block on the screen. The original implementation had 8 rows of 14 bricks, whose point value is based on its color. The speed of the ball would increase at specific intervals. My version begins with 5 rows of 16 bricks. I only have a monochrome display, so the bricks are the same color, and for simplicity, they're worth the same value. The ball changes velocity depending on how it collides with the paddle and the bricks. User input is 2 buttons. Pressing one button will move the paddle to the left. Pressing the other button will move the paddle to the right. Pressing both buttons simultaneously will serve the ball. This is the block diagram for the system. When the STM32 board boots, it will fetch the first level from the EEPROM. The main loop will draw the brick array, then write the lives remaining, the score, then draw the ball and the paddle. Finally, we'll check the status of the buttons and serve the ball or move the paddle accordingly. If a level is cleared, the STM32 board will fetch the next level and update the display. This is a realization of the game. As you can see, there's not much to it, as the EEPROM and the OLED both use I2C, needing only power, ground, clock, and data lines. The OLED here uses a STEMMA QT connector going to power and ground here, and the clock and data here. The EEPROM has its data line here, and the clock snakes around over through here, and these are its power and ground lines. This is the input for the right button. The left button input is hidden under here, and they both have pull-down resistors. These are the main components of the game. It starts with a STM32 Nucleo board. I set up to use both I2C buses. I had to set the clock frequency for both buses to match because for some reason it wouldn't work if they were different. The EEPROM can store 4 kilobytes of data, which in this implementation is approximately 400 levels. Each level is read by calling ST's HAL library call, HAL I2C memread, and giving it the correct address. The OLED display is a 1-inch diagonal, 128 by 64 pixels. The driver for the display is written by GitHub user Apiscon, so I just needed to call fill rectangle, fill circle, and write string. To get the status of the buttons, I call HAL GPO read pin for each button. Test cases consist of winning the game or intentionally losing at different points and watching for anomalies. The games here are sped up dramatically, as the 3 levels currently programmed can take over 10 minutes to complete. The embedded aspect of this project wasn't too complicated, as the implementation followed the labs pretty closely. The gameplay code ate up most of the development time, specifically the collision detection and reaction, which could be better. Sometimes a ball would get up into the bricks and move unnaturally, other times it would bounce vertically indefinitely. If I were to continue this project, I would revisit the collision detection and resolve these issues. Also, I'd develop a level updater with a GUI to generate the bytecodes for the level and a means to write the level to the EEPROM. I could also implement a section where the higher score is written to the EEPROM and stored indefinitely. These are my references. Special thanks to learnopengl.com for the collision detection, even though it's in C++. I use the Games Physics Cookbook to help translate it to C. Thank you for watching.